Black holes have long captured our imagination and challenged our understanding of the universe. From their immense gravitational pull to their ability to warp space-time, black holes are a source of endless fascination and mystery. In this video, we'll embark on a journey into the heart of black holes, exploring their formation, their properties, and their role in the universe. We'll delve into the groundbreaking discoveries that have shaped our understanding of these celestial objects. From Einstein's theory of general relativity to the recent detection of gravitational waves and the first image of a black hole shadow. We'll also consider the mind-bending implications of black holes, from the possibility of time travel and wormholes to the existence of parallel universes and the ultimate fate of the universe itself. We'll also explore the ongoing research that seeks to unravel the mysteries of these cosmic giants, pushing the boundaries of our knowledge and challenging our perception of reality. And who knows, perhaps the next big discovery in black hole physics will be made by someone watching this video right now. Imagine a region of space where the fabric of reality itself is warped and twisted so intensely that anything that ventures too close, whether it's a planet, a star, or even light itself, gets trapped and pulled in, never to be seen again. That's the essence of a black hole. Einstein's theory of general relativity tells us that if you squeeze enough mass into a small enough space, it will create a black hole. The boundary of this region where the escape velocity exceeds the speed of light is called the event horizon. Once you cross the event horizon, there's no turning back. You're doomed to be pulled towards the black hole's center, where all the matter is crushed into an infinitely dense point called a singularity. The idea of black holes was first proposed back in the 18th century, but it wasn't until the 20th century that scientists started taking them seriously. The discovery of neutron stars, which are incredibly dense objects formed from the collapsed cores of massive stars, made the idea of black holes seem more plausible. And in 1971, the first black hole was discovered, known as Cygnus X1. Since then, we found many more black holes, both small ones formed from the death of stars and supermassive ones lurking at the center of galaxies. We can't see black holes directly because they don't emit light, but we can detect their presence by observing their effects on their surroundings. For example, matter falling into a black hole forms a swirling disk around it, called an accretion disk, which gets incredibly hot and emits powerful X-rays. We can also see the effects of a black hole's gravity on nearby stars, causing them to orbit in unusual ways. In recent years, scientists have even managed to capture the first ever image of a black hole shadow, a dark silhouette against a backdrop of glowing gas. This groundbreaking image provided direct evidence for the existence of black holes and confirmed many of the predictions of Einstein's theory of general relativity. The idea of a black hole didn't just appear out of nowhere. It has a fascinating history that traces back to the 18th century, when an English clergyman named John Michell first pondered the possibility of such a cosmic behemoth. Michell, a pioneer in astronomy, had a simple yet groundbreaking idea. What if there were stars so massive that their gravity was strong enough to trap light itself? He did some calculations, assuming that these hypothetical stars had the same density as our sun, and came to a startling conclusion. If a star's diameter were 500 times larger than the sun's, its gravity would be so powerful that light wouldn't be able to escape. Mitchell called these objects dark stars, and he even suggested that we might be able to detect them indirectly through their gravitational effects on nearby visible stars. At the time, this idea was met with a mix of excitement and skepticism. Some scientists were intrigued by the possibility of these invisible giants lurking in the universe, while others questioned whether gravity could truly affect light, which was then thought to be a wave, not a particle. Fast forward to the early 20th century, and Einstein's theory of general relativity revolutionized our understanding of gravity. This theory showed that gravity isn't just a force pulling on objects, but rather a curvature of spacetime itself. In this new framework, Mitchell's idea of light being slowed down and falling back to the surface of a massive star was replaced by a more elegant explanation. Light travels along the curved paths of spacetime, and near a black hole, these paths curve so sharply that light can't escape. The modern understanding of black holes emerged from the groundbreaking work of Albert Einstein and his theory of general relativity. In 1915, Einstein published his theory, which revolutionized our understanding of gravity, describing it not as a force, but as a curvature of spacetime caused by mass and energy. Just a few months later, Karl Schwarzschild, a German physicist serving in the German army during World War I, found a solution to Einstein's field equations that described the gravitational field of a point of mass and a spherical mass. This solution, known as the Schwarzschild metric, revealed a peculiar behavior at a certain radius, later called the Schwarzschild radius. At this radius, the equations seemed to break down, leading to a singularity where some terms became infinite. The nature of the singularity and its physical implications remained a mystery for several years. In 1924, Arthur Eddington, a British astronomer, showed that the singularity could be removed by a clever change of coordinates, suggesting that it might not be a real physical phenomenon. In 1933, Georges Lemaître, a Belgian priest and physicist, further clarified this issue, recognizing that the singularity at the Schwarzschild radius was a coordinate singularity, an artifact of the chosen coordinate system rather than a genuine physical singularity. Despite these theoretical advancements, the idea of a black hole remained largely a mathematical curiosity. It wasn't until the 1960s that theoretical work by physicists like Roger Penrose and Stephen Hawking demonstrated that black holes were a generic prediction of general relativity, not just a special case. The discovery of neutron stars in 1967 further fueled the interest in black holes as a potential astrophysical reality. In 1939, J. Robert Oppenheimer and his colleagues explored the theoretical possibilities of a star collapsing under its gravity to form a black hole. They used Einstein's theory of general relativity to model this process and conclude that if a star's mass exceeded a certain limit, known as the Tolman-Oppenheimer-Volkoff limit, no known physical law could prevent its collapse into a black hole. Interestingly, Oppenheimer and his co-authors initially interpreted the singularity at the Schwarzschild radius as a boundary where time stopped, a perspective that's valid for external observers but not for those falling into the black hole. They referred to these hypothetical collapsed stars as frozen stars, because from an outside perspective, their surfaces would appear to freeze in time at the moment of collapse. However, just months earlier, Einstein himself had attempted to disprove the existence of black holes using his own theory of general relativity. In his paper on a stationary system with spherical symmetry consisting of many gravitating masses, Einstein argued that such objects were physically impossible. The resolution of this apparent conflict came later in 1939, when Oppenheimer and his student Hartland Snyder published their groundbreaking paper on continued gravitational contraction. This paper, which made no reference to Einstein's earlier work, used general relativity to describe the process of stellar collapse and the formation of a black hole, providing the first detailed theoretical model of these massive objects. The Oppenheimer-Snyder model, while a significant breakthrough, also highlighted the challenges of understanding the extreme conditions within a black hole. The singularity at its center, where the laws of physics as we know them break down, remains a mystery that continues to challenge physicists and inspire new theoretical frameworks like quantum gravity. The golden age of black hole research dawned in the mid-20th century, a period of groundbreaking discoveries and theoretical advancements that solidified our understanding of these massive objects. In 1958, David Finkelstein made a crucial breakthrough by identifying the Schwarzschild surface, the boundary of a black hole, as an event horizon. This point of no return marked the edge of a region from which nothing, not even light, could escape. This concept, while building upon earlier work, provided a clearer picture of the black hole's structure and its implications for the fate of matter and energy that ventured too close. This period also saw the discovery of pulsars, rapidly rotating neutron stars, in 1967. These incredibly dense objects, formed from the collapsed cores of massive stars, provided further evidence for the existence of black holes and spurred a renewed interest in studying the extreme gravitational environments that can arise from stellar collapse. Throughout the 1960s, physicists like Roy Kerr and Ezra Newman found more general solutions to Einstein's field equations, describing black holes that were not only static, but also rotating and electrically charged. These solutions, known as the Kerr and Kerr-Newman metrics, expanded our understanding of the possible properties and behaviors of black holes. The no-hair theorem, developed by Werner Israel, Brandon Carter, and David Robinson, further refined our understanding of black holes. This theorem states that a stationary black hole is completely characterized by three parameters: its mass, angular momentum, or spin, and electric charge. This implies that all other information about the matter that formed the black hole is lost once it crosses the event horizon, a concept that would later lead to the black hole information paradox. Initially, some physicists believed that the strange and seemingly paradoxical features of black hole solutions were merely mathematical artifacts arising from the idealized symmetry conditions used in the calculations. However, in the late 1960s, Roger Penrose and Stephen Hawking, using powerful mathematical techniques, proved that singularities, or points of infinite density, are a generic feature of black holes, not just a theoretical curiosity. This groundbreaking work earned Penrose a share of the 2020 Nobel Prize in Physics. In the early 1970s, observations of a galactic X-ray source known as Cygnus X1 provided the first strong evidence for the existence of a black hole. This discovery, along with the subsequent observations of other black hole candidates, confirmed that these objects were not just theoretical constructs, but actual physical entities in the universe. The golden age of general relativity also saw the development of black hole thermodynamics, a field of study that explores the surprising connection between black holes and the laws of thermodynamics. Pioneering work by James Bardeen, Jacob Bekenstein, Brandon Carter, and Stephen Hawking led to the formulation of the 4 laws of black hole mechanics, which describe the behavior of black holes in terms of their mass, entropy, and surface gravity. In 1974, Hawking made another groundbreaking discovery. Black holes are not entirely black. They actually emit a faint radiation, known as Hawking radiation, which has a thermal spectrum, similar to the radiation emitted by a hot object. This discovery further solidified the connection between black holes and thermodynamics, and raised profound questions about the fate of information that falls into a black hole, leading to the black hole information paradox. In 2016, the LIGO and Virgo collaborations announced the first ever direct detection of gravitational waves, ripples in the fabric of spacetime caused by the collision of 2 black holes billions of light years away. This groundbreaking discovery not only confirmed the existence of black holes, but also opened up a new window into the universe, allowing us to hear the echoes of these cataclysmic events. Then, in 2019, the Event Horizon Telescope, a network of radio telescopes around the world, captured the first ever image of a black hole. This iconic image, showing a dark silhouette against a backdrop of swirling light, provided direct visual evidence for the existence of black holes and validated many of the predictions of general relativity. While these groundbreaking observations have brought black holes into the realm of the observable, most black holes remain hidden from view. They're solitary and don't emit any radiation, making them incredibly difficult to detect. However, scientists believe that there could be hundreds of millions of black holes lurking in our own Milky Way galaxy alone. One way to detect these hidden black holes is through gravitational lensing, a phenomenon where the gravity of a massive object, like a black hole, bends and distorts the light from objects behind it. By observing these distortions, astronomers can infer the presence of a black hole even if it's not directly visible. As of 2023, the closest known black hole to Earth is Gaia BH1, located about 1,560 light-years away. This relatively nearby black hole, discovered using data from the Gaia spacecraft, is thought to be about 10 times the mass of our Sun. The name black hole is surprisingly recent, considering how long we've been fascinated by these cosmic enigmas. Early on, they were called things like dark stars or gravitationally collapsed objects. Not exactly the catchiest names, right? But then, in the early 1960s, physicist Robert H. Dick reportedly made a comparison that stuck. He likened these mysterious objects to the Black Hole of Calcutta, a notorious prison in India where people entered but rarely came out alive. The term black hole started appearing in print around 1963, and it really took off after a lecture by physicist John Wheeler in 1967. Wheeler liked the term because it was short, memorable, and captured the essence of these objects. They're black because light can escape, and they're like holes because things fall in and don't come out. The no-hair theorem tells us that once a black hole settles down after its formation, it's basically a cosmic blank slate. You can't tell what went into making it, whether it was a star, a planet, or even a giant pile of space dust. All that's left are 3 basic properties. 1 being mass, how much stuff is packed into the black hole. 2 is electric charge, whether it has a positive or negative charge, or none at all. And number 3 is its angular momentum, which is how fast it's spinning. This no-hair idea means that if you have two black holes with the same mass, charge, and spin, they're basically twins, even if they were formed from completely different things. These 3 properties are special because we can observe them from the outside. For instance, a charged black hole will push or pull on other charged objects, just like any other charged thing. We can also measure a black hole's mass by looking at how its gravity affects nearby stars and its spin by observing how it drags space-time around it. But here's the catch. Anything that falls into a black hole loses its individuality. All the information about its shape, composition, and even the particles it was made of gets spread out evenly across the black hole's event horizon. This loss of information is a real head-scratcher for physicists. It seems to violate a core principle of both classical and quantum physics, which says that you should be able to trace the history of a system forward or backward in time if you have enough information about it. But with black holes, it seems like that information is gone forever, creating a paradox that has puzzled scientists for decades. This is the infamous black hole information paradox, a clash between our understanding of gravity and the quantum world. The search for a resolution to this paradox is ongoing, and it has led to some mind-bending ideas like the possibility that information is somehow encoded on the black hole's event horizon or even stored in a parallel universe. Okay, so we know black holes are these crazy objects with super strong gravity, but what exactly are their defining characteristics? Well, the simplest kind of black hole is like a cosmic vacuum cleaner with only one setting. It has mass, but no electric charge or spin. These are called Schwarzschild black holes, and they're perfectly spherical like a ball. The cool thing about them is that from a distance, their gravity feels exactly the same as any other spherical object with the same mass. So, if you replace the sun with a Schwarzschild black hole of the same mass, the Earth would keep orbiting it just like it does now. Of course, if you got too close to the black hole, things would get messy. But that's a story for another time. Now, there are also more complex black holes out there. Some have electric charge, some spin, and some even have both. But no matter what, their charge and spin can't be too big compared to their mass. There's a limit set by Einstein's equations, beyond which things get weird and the black hole might not even have an event horizon. Most black holes that form from dying stars are expected to have very little charge, but they usually do spin. And there's even a black hole out there that seems to be spinning almost as fast as physically possible. Black holes are often classified based on their mass. The size of a black hole, determined by its event horizon, is directly related to its mass. The more massive the black hole, the bigger its event horizon. For a non-spinning uncharged black hole, we can calculate the size of its event horizon by using a simple formula. But if the black hole is spinning or has charge, the event horizon gets a bit smaller. So while their immense gravity can warp space-time and create some truly mind-bending phenomena, they still have to follow the rules of physics, just like everything else in the universe. The event horizon gets its name because any events that happen beyond it are essentially hidden from the outside universe. We can't see or detect what's happening inside, making it impossible to know for sure what lies beyond that mysterious threshold. Einstein's theory of general relativity explains how massive objects like black holes warp the fabric of space-time itself. This warping causes the paths of objects and even light to bend towards the massive object. At the event horizon of a black hole, this warping becomes so extreme that all paths lead inwards, towards the black hole's center. From a safe distance, if you were watching an object fall into the black hole, you'd see something strange. The object would seem to slow down as it approaches the event horizon, and its light would become increasingly red and dim. Eventually, the object would appear to freeze in time, fading away until it completely disappears from view. This is due to the intense gravitational field near the black hole, which stretches and distorts both space and time. But here's the mind-bending part. If you were the one falling into the black hole, you wouldn't experience any of this strange behavior. From your perspective, time would seem to tick normally, and you'd cross the event horizon without even noticing it. In fact, according to classical general relativity, you wouldn't be able to tell where the event horizon is just by looking around you. This is because the laws of physics, as experienced by an observer in freefall, are the same everywhere in the universe, even near a black hole. This is known as Einstein's equivalence principle, and it's one of the cornerstones of general relativity. The event horizon of a black hole, while invisible to those crossing it, is a crucial boundary that separates the inside of the black hole from the outside universe. Its topology, or shape, is always spherical when the black hole is stable. For a non-rotating black hole, the sphere is perfectly round, while for a spinning black hole, it becomes slightly flattened at the poles, like a spinning basketball. At the very heart of a black hole, nestled deep within its event horizon, lies a mind-boggling concept: the singularity. According to Einstein's theory of general relativity, this is a region where spacetime becomes infinitely curved, and all the matter that falls into the black hole gets compressed into an unimaginably tiny point. It's like trying to squeeze the entire Earth into a grain of sand. For a non-rotating black hole, the singularity is a single point, a place where the laws of physics as we know them break down. For a spinning black hole, things get even weirder. The singularity is smeared out into a ring shape, rotating along with the black hole itself. If you were unfortunate enough to fall into a non-rotating black hole, there's no escape. Once you cross the event horizon, you're inexorably drawn towards the singularity, where you'd be crushed into an infinitely dense point. Even if you try to slow your descent by firing your spaceship's engines, it wouldn't matter. The tidal forces near the singularity are so strong that they would stretch you out like spaghetti, a process aptly called spaghettification. But what about charged or rotating black holes? Here, things get a bit more interesting, at least in theory. Some solutions to Einstein's equations suggest that it might be possible to avoid the singularity and even merge into a different spacetime, with the black hole acting as a sort of cosmic wormhole. This idea has fueled countless science fiction stories about traveling to other universes or even back in time. However, it's important to remember that these are just theoretical possibilities. Any slight disturbance or imperfection in the black hole would likely destroy this delicate wormhole structure. The appearance of singularities in general relativity is a sign that the theory breaks down at these extreme conditions. This is not surprising, as we expect quantum mechanics, the theory of the very small, to take over when things get incredibly dense and compact, like at the center of a black hole. The challenge for physicists is to develop a theory of quantum gravity that can seamlessly merge the laws of gravity with the principles of quantum mechanics, hopefully resolving the singularity problem and providing a more complete understanding of the universe's most extreme objects. Now, let's talk about another intriguing feature of black holes: the photon sphere. Imagine a black hole as a cosmic whirlpool, sucking everything in its vicinity. The photon sphere is like a ring around this whirlpool, where light itself gets trapped in a never-ending loop. It's a boundary where photons, the particles of light, can orbit the black hole in a circular path. But it's a precarious balance. Any slight disturbance, like a stray particle of matter, can knock the photon off its orbit, either sending it spiraling into the black hole or flinging it back out into space. The photon sphere is a fascinating region because it's the closest you can get to a black hole and still have a chance of escaping. Light that originates from within the photon sphere is doomed to be captured by the black hole's gravity, but light that passes through the photon sphere from the outside can still make its way back out into the universe. This means that any light we detect from the vicinity of a black hole must come from the objects between the photon sphere and the event horizon. The radius of the photon sphere depends on the black hole's mass, and for rotating black holes, also on its spin. The faster the black hole spins, the more distorted the photon sphere becomes. Rotating black holes, unlike their static counterparts, possess a unique and dynamic region surrounding them known as the ergosphere. This region, shaped like a flattened sphere, is a zone where spacetime itself is dragged along the black hole's rotation. The ergosphere is a consequence of a phenomenon called frame dragging, predicted by Einstein's theory of general relativity. It states that any rotating mass from a spinning top to a massive black hole will slightly drag the surrounding spacetime along with it. This means that any object near a rotating mass will tend to start moving in the direction of its rotation, even if it's initially at rest. Near the event horizon of a rotating black hole, this frame dragging effect becomes so intense that an object would need to travel faster than the speed of light in the opposite direction just to stay in place. This creates a region where it's impossible to stand still. You're inevitably swept along by the swirling currents of space-time. The ergosphere extends beyond the event horizon, reaching its furthest point at the black hole's equator and coinciding with the event horizon at its poles. This creates a distorted, flattened shape reflecting the influence of the black hole's rotation on the surrounding space-time. While objects and radiation can still escape from the ergosphere, they can also experience some peculiar effects. Through the Penrose process, objects can extract energy from the rotating black hole as they pass through the ergosphere. This extracted energy comes at the expense of the black hole's rotational energy, causing it to slow down slightly. A variation of the Penrose process, called the Blandford-Nyack process, occurs in the presence of strong magnetic fields around a black hole. This process is believed to be responsible for the powerful jets of energy and matter observed in quasars and other active galactic nuclei. Let's imagine a black hole as a cosmic drain, with its powerful gravity pulling everything towards its center. Now, in the world of classical physics, as described by Newton, objects can orbit a central body, like a black hole, at any distance, as long as they have the right speed. It's like planets orbiting the sun. They stay in their paths because their speed balances the sun's gravity. But Einstein's general relativity throws a wrench into this picture. It tells us that there's a limit to how close you can get to a black hole and still maintain a stable orbit. This limit is called the innermost stable circular orbit, or ISCO. Think of it like a whirlpool. You can safely swim in circles around the edge, but if you get too close to the center, the current will inevitably pull you in. Likewise, if an object orbiting a black hole gets closer than the ISCO, even the slightest nudge will send it spiraling into the black hole's grasp. The location of this ISCO depends on the black hole's spin. For a non-rotating black hole, it's located at a distance 3 times the Schwarzschild radius. But here's the interesting part. If the black hole is spinning, the ISCO gets closer to the event horizon. So, the faster the black hole spins, the closer you can get before being pulled in. The ISCO is an important concept in understanding how matter behaves around black holes. It marks the inner edge of accretion disks. Matter within the ICO is destined to fall into the black hole, releasing tremendous amounts of energy in the process. Beyond the ISCO lies the final frontier of a black hole's gravitational domain, the plunging region. This is where things get really intense. Once an object enters this region, there's no turning back. In the plunging region, matter can no longer maintain a stable orbit around the black hole. It's forced to spiral inwards, accelerating rapidly towards the black hole's center, approaching the speed of light as it gets closer and closer. Imagine a spaceship venturing too close to a black hole. Once it crosses the ISCO, its engines wouldn't be powerful enough to counteract the black hole's immense gravity. The ship would be helplessly pulled inward, its crew witnessing the distortion of space and time as they hurtle towards the singularity. The idea of black holes, with their extreme gravity and event horizons, was so bizarre that for a long time, even Einstein himself doubted they could actually exist. He thought that something would always prevent stars from collapsing completely, keeping them from turning into these cosmic monsters. This skepticism led many scientists to dismiss the possibility of black holes for years. But a few stubborn researchers kept digging deeper, convinced that these strange objects were more than just mathematical curiosities. Eventually, in the 1960s, they managed to convince the majority of physicists that black holes were not only possible, but were actually a natural consequence of Einstein's theory of general relativity. This shift in thinking was partly fueled by the discovery of neutron stars. These discoveries showed that nature could indeed create objects with incredibly strong gravity, making the existence of black holes seem much more plausible. But the story doesn't end there. Roger Penrose, a brilliant mathematician and physicist, proved that once an event horizon forms around a collapsing star, a singularity, a point of infinite density, must always form at its center. This singularity is where the laws of physics as we know them break down. Stephen Hawking then took it a step further. He showed that even the universe itself might have started from a singularity, the Big Bang, without the need for any exotic matter or special conditions. These theoretical breakthroughs, along with the discovery of the laws of black hole thermodynamics, transformed black holes from mere mathematical oddities into legitimate objects of scientific inquiry. Now, the most common way black holes form is through the collapse of massive stars. When a star runs out of fuel, its core collapses under its gravity. And if the star is massive enough, this collapse can lead to the formation of a black hole. But that's not the only way. Black holes can also form through other processes, like the merger of 2 neutron stars or the direct collapse of massive gas clouds in the early universe. So, while the idea of black holes might have started as wild speculation, it has now become a cornerstone of modern astrophysics, supported by both theoretical models and observational evidence. Now, for most stars, this collapse stops at a certain point, and they end up as incredibly dense objects like white dwarfs or neutron stars. But for really massive stars, the collapse doesn't stop. The gravity is so strong that it keeps squeezing the star's core until it becomes infinitely small and dense, a black hole. Scientists believe that these stellar mass black holes, formed from the death of massive stars, are just one type of black hole. There are also supermassive black holes, millions or even billions of times more massive than our Sun, lurking at the center of galaxies. These giants are thought to have formed in the early universe, either through the collapse of massive gas clouds or the merging of smaller black holes. They play a crucial role in the evolution of galaxies, influencing the motion of stars and even triggering the formation of new stars. The process of gravitational collapse that leads to a black hole is a violent and energetic one. Most of the energy is released quickly, but from the outside, it looks like the star is slowly fading away. This is because the intense gravity near the black hole slows down time, making it seem like the collapse is happening in slow motion. The light from the collapsing star also gets stretched and its color shifts towards the red end of the spectrum, a phenomenon known as gravitational redshift. Eventually, the light becomes so faint that we can no longer see it, and the star seems to disappear from view. This creates the illusion of a frozen star, where the surface of the star appears to be stuck in time at the moment it crosses the event horizon. But in reality, the collapse continues, and the star's matter is drawn towards the singularity at the black hole's core. The intense conditions of the early universe, just moments after the Big Bang, could have led to the formation of a special type of black hole, primordial black holes. Now, to create a black hole, you need to squeeze a lot of stuff into a tiny space, making it incredibly dense. In today's universe, we usually see this happen when massive stars collapse at the end of their lives. But in the early universe, things were much more compact and dense, potentially allowing for black holes to form directly without needing a star to collapse first. However, just having a high density isn't enough. You also need some unevenness, or clumps in the distribution of matter. These clumps can then act as seeds for black holes, pulling in more and more matter with their gravity until they become these inescapable cosmic traps. Different models of the early universe predict different sizes for these primordial black holes, ranging from incredibly tiny ones to ones even larger than supermassive black holes. Now you might be wondering, if the early universe was so dense, why didn't it all just collapse into one giant black hole? Well, the universe was also expanding rapidly, and this expansion outpaced the pull of gravity, preventing a total collapse. While we've mainly talked about black holes forming when massive stars collapse, there's another way that they could theoretically be created, through incredibly powerful collisions of particles. Imagine two tiny particles smashing into each other at near the speed of light. If they collide with enough energy, they could, in theory, create a black hole. It's like squeezing two grains of sand together so hard that they collapse into a tiny, invisible void. However, as of now, we haven't seen any evidence of such black holes being created, even in the most powerful particle accelerators like the Large Hadron Collider. This suggests that there's a minimum size or mass required for a black hole to form. Scientists think this limit might be around the Planck mass, which is an incredibly tiny mass scale where the effects of quantum gravity become important. This means that creating black holes and particle collisions would require energies far beyond what we can currently achieve. However, some theories suggest that the minimum black hole mass could be much lower, potentially within the reach of cosmic rays hitting the Earth's atmosphere or even experiments at the Large Hadron Collider. These are still speculative ideas, and most experts believe the chances of actually creating black holes in these scenarios are pretty slim. But even if we did manage to create micro black holes, they wouldn't be a threat. They're predicted to evaporate almost instantly, disappearing into a tiny puff of Hawking radiation before they could cause any harm. Once a black hole is born, it's not content to just sit there. Like a cosmic Pac-Man, it keeps gobbling up more and more matter from its surroundings. This constant feeding frenzy is how black holes grow and get bigger. Scientists believe that this process of growth is how some of the supermassive black holes at the center of galaxies got so incredibly huge. They started out small, maybe from the collapse of a massive star, and then gradually grew by devouring everything around them. But it's not just about eating stars and gas. Black holes can also merge with each other, combining their masses to create even bigger monsters. This is thought to have played a major role in the early universe, when even smaller black holes collided and merged to form the supermassive ones we see today. One of the most mind-bending aspects of black holes is that they're not entirely black. In 1974, Stephen Hawking made the surprising prediction that black holes actually emit a faint glow of radiation, known as Hawking radiation. This radiation is like a slow leak of energy from the black hole, and it has some pretty wild consequences. Imagine a black hole as a giant pot of water. Hawking radiation is like the steam rising from the pot, carrying away a tiny bit of its energy with each puff. Over vast periods of time, the steady stream of radiation can cause the black hole to shrink and eventually evaporate completely. The temperature of this Hawking radiation is incredibly low, especially for massive black holes. A typical stellar black hole, formed from the collapse of a star, has a temperature of just a few billionths of a Kelvin. That's way colder than the already chilly cosmic microwave background radiation that fills the universe. This means that most black holes are actually gaining more energy from the surrounding radiation than they're losing through Hawking radiation. So, they're actually growing, not shrinking. Only really tiny black holes, with masses less than the moon, would have a temperature high enough to evaporate. These miniature black holes, if they exist, would be incredibly hot and would disappear in a flash, releasing a burst of energy. Hawking radiation is so faint that it's incredibly difficult to detect directly. However, scientists are still looking for signs of it, especially in the form of gamma ray bursts that might be emitted in the final moments of small black holes' evaporation. Black holes don't give off any light or any other kinds of radiation that we can easily see. So, how do we even know they're there? Astronomers look for telltale signs of a black hole's presence by observing how it interacts with its surroundings. One way is to look for its gravitational influence. If a black hole is lurking nearby, its powerful gravity will tug on nearby stars and gas, causing them to move in unusual ways. By carefully observing these motions, astronomers can infer the presence of a black hole, even if they can't see it directly. One of the most exciting projects is the Event Horizon Telescope. Imagine it as a giant virtual telescope, created by linking together radio telescopes all over the world. This massive network allows astronomers to zoom in on the regions right around the black hole's event horizon with incredible detail. In 2017, the EHT focused its attention on the supermassive black hole at the center of a galaxy called Messier 87. They collected tons of data over several days, and after 2 years of painstaking processing, they released the first ever direct image of a black hole. Now you might be thinking, but black holes are black. How can you even take a picture of something that doesn't emit light? Well, the image doesn't actually show the black hole itself. It shows the glowing gas swirling around the black hole's edge, just before it gets sucked in. This gas is superheated and emits radiation that we can detect with the EHT. The image shows a dark central region, which is the black hole's shadow, surrounded by a bright ring of light. This ring is actually the light from the far side of the accretion disk being bent and distorted by the black hole's intense gravity. In 2022, the EHT also captured an image of Sagittarius A, the supermassive black hole at the center of our own Milky Way galaxy. This was even more challenging than imaging M87 because Sagittarius A is much smaller and its surroundings are more turbulent. But the image still revealed the same telltale signs of a black hole, a dark shadow surrounded by a ring of light. These groundbreaking images have provided direct evidence for the existence of black holes and confirmed many of the predictions of Einstein's theory of general relativity. They've also given us a glimpse into the extreme environments near black holes, where matter is swirling at incredible speeds and magnetic fields are twisted and tangled. In 2023, the EHT even managed to capture an image of a black hole shadow and its powerful jet of energy, a spectacular display of the forces at play near these cosmic behemoths. For a long time, we could only theorize about black holes, but in 2015, scientists made a monumental breakthrough. Using LIGO, they detected gravitational waves for the first time. The signal they detected matched perfectly with what we'd expect from two black holes spiraling towards each other and merging into one. This discovery was a huge deal because it gave us the most concrete evidence yet that black holes are real. The signal also told us a lot about those black holes. For example, it showed that they were incredibly close together right before they merged, which meant that they had to be incredibly dense objects, exactly what we'd expect from black holes. But the most exciting part of the signal was the ring down. This is the final stage of the merger, where the newly formed black hole settles down into a stable state. It's like the aftershock of an earthquake, and it's the most direct way we can see a black hole. By analyzing the ring down signal, scientists can figure out the mass and spin of the final black hole, which matches predictions from computer simulations. This further confirms that what we've seen is indeed a black hole. This discovery also gave us the first proof that black holes can exist in pairs. It also showed us that black holes can be much more massive than we previously thought, opening up new questions about how they form and evolve. One of the most compelling pieces of evidence for the existence of black holes lies in the heart of our very own Milky Way galaxy, By carefully tracking the movements of stars near the galactic center, astronomers have observed them whirling around an invisible object with tremendous gravitational pull. Since 1995, astronomers have been observing about 90 stars orbiting this mysterious object, which coincides with a strong radio source called Sagittarius A. By analyzing their orbits and applying Kepler's laws of planetary motion, scientists were able to calculate the mass of this invisible object. The results were astounding. They estimated that an object with a mass of about 4.3 million times that of our Sun must be lurking there, crammed into a space smaller than our solar system. Now, what kind of object could pack that much mass into a tiny volume? The only plausible explanation is a supermassive black hole. No other known object could exert such a powerful gravitational pull without being visible. Observations also suggest that this object might even have an event horizon. Black holes are not just passive objects. They're actively feeding on matter and energy from their surroundings. This process, called accretion, is like a cosmic whirlpool, where gas and dust spiral towards the black hole, creating a swirling disk of material. Now, you might picture this accretion disk as a flat, pancake-like structure orbiting the black hole, but it's not that simple. The black hole's intense gravity warps and distorts the disk, creating a mind-bending visual spectacle that's far from the simple image we might imagine. As matter swirls closer and closer to the black hole, friction within the disk causes it to heat up dramatically. This superheated material emits intense radiation, mostly in the form of X-rays. These X-rays can be detected with telescopes, providing astronomers with clues about the presence and properties of the black hole. Accretion is an incredibly efficient way to generate energy. Up to 40% of the matter falling into a black hole can be converted into energy, far more than the 0.7% efficiency of nuclear fusion that powers stars. In some cases, black holes also produce powerful jets of energy and matter that shoot out from their poles at nearly the speed of light. These jets, while not fully understood, are believed to be connected to the accretion process and the black hole's magnetic field. The immense energy released during accretion is responsible for some of the most spectacular phenomena in the universe. Quasars, for example, are incredibly bright objects powered by the accretion disks of supermassive black holes at the centers of galaxies. X-ray binaries, another type of energetic system, are formed when normal stars orbit a black hole or neutron star. The compact object pulls material from its companion star, creating an accretion disk that emits powerful X-rays. Even stars themselves can be torn apart by the tidal forces of a supermassive black hole in a dramatic event called a tidal disruption event. Some of the stellar debris forms an accretion disk around the black hole, emitting a bright flare of radiation that astronomers can observe. In 2011, scientists made the first direct observation of a quasar accretion disk around a supermassive black hole, providing further evidence for the role of accretion in powering these energetic phenomena. While black holes are masters of disguise, their insatiable hunger for matter can sometimes give them away. X-ray binaries, systems where a normal star orbits a compact object like a black hole or neutron star, offers a unique opportunity to detect and study these elusive objects. As the black hole's intense gravity pulls material from its companion star, it creates an accretion disk. Friction within this disk heats the material to incredibly high temperatures, causing it to emit powerful X-rays. These X-rays can be detected by telescopes, revealing the presence of the black hole. If we can detect signals coming directly from the compact object at the center of the X-ray binary, we know it can't be a black hole. Remember, black holes don't let anything, not even light, escape. So any signal we detect must be coming from something else, like a neutron star. On the other hand, if we don't detect any signals from the compact object, it could be a black hole, but we need more evidence to be sure. By carefully studying the companion star and its orbit, astronomers can estimate the mass of the compact object. If this mass is way too big for a neutron star, then it's very likely a black hole. Cygnus X1 was the first black hole found using this method. One particularly interesting class of X-ray binaries is called soft X-ray transients. In these systems, the companion star is relatively small, making it easier to accurately measure the black hole's mass. These systems also have periods of low X-ray emission, allowing astronomers to study the companion star in more detail and gather more precise information about the black hole's properties. Sometimes, the X-ray emissions from those swirling accretion disks around black holes get a little jittery. They start to flicker at certain frequencies. Scientists call these signals quasi-periodic oscillations, or QPOs. Think of it like a spinning record with a slight warp. As the record spins, the needle jumps and skips, creating a repeating pattern of sound glitches. Likewise, QPOs are thought to be caused by clumps of matter orbiting very close to the black hole at the innermost stable circular orbit. The frequency of these flickers is directly related to the black hole's mass. A more massive black hole will have a lower QPO frequency, while a smaller black hole will have a higher frequency. This means that by measuring the frequency of these QPOs, astronomers can get another way to estimate the mass of the black hole. They offer an independent way to confirm the mass estimates obtained from other methods, like observing the orbits of nearby stars. Some galaxies throw out wild bursts of energy and radiation. Astronomers call these active galaxies, and they're a bit different from the quieter galaxies like our own Milky Way. Scientists think that these bursts at the center of these active galaxies is powered by a supermassive black hole. A black hole millions or even billions of times more massive than the ones formed from dying stars. These active galactic nuclei, or AGNs, have a specific structure. At the center is the supermassive black hole. Surrounding it is the accretion disk. Shooting out from the top and bottom of the disk are two jets of high-energy particles. These jets can extend for thousands of light years, blasting their way through the galaxy. While scientists believe that most galaxies, even the quiet ones, have a supermassive black hole at their center, only a few have been studied closely enough to actually measure the mass of their central black hole. The connection between these supermassive black holes and their host galaxies is pretty strong. There's a relationship between the mass of the black hole and how fast the stars in the galaxy's central bulge are moving. This suggests that the black hole and the galaxy grew up together, influencing each other's formation and evolution. Besides looking at how black holes make things move, there's another way to spot them, by observing how they bend light. Massive objects like black holes warp the fabric of spacetime around them, and this warping can act like a lens, bending and distorting the light from objects behind them. This is called gravitational lensing. A black hole's gravity can magnify and distort the light from distant stars or galaxies, creating weird and wonderful visual effects. Astronomers have observed this phenomenon in a few different ways, such as weak gravitational lensing. This is when the light is bent just a little bit, causing a slight shift in the position of distant objects, as well as microlensing. This happens when the light source is too far away to see clearly, but its brightness is amplified by the black hole's gravity. In 2022, astronomers might have even seen a microlensing event caused by a lone black hole, which would be a pretty big deal. And stars orbiting a black hole. By observing how stars move around a black hole, we can see the effects of its gravity and use that to estimate its mass and location. One place where astronomers are actively looking for these effects is around Sagittarius A. There are several stars orbiting it, and by carefully tracking their movements, scientists hope to learn more about this hidden giant and how it interacts with its surroundings. The evidence for black holes, while strong, isn't completely airtight. There's still room for alternative explanations, especially when it comes to the smaller stellar mass black holes. What if there are other exotic forms of matter that can resist collapse, even at incredibly high densities? Scientists have proposed some hypothetical objects that could mimic the behavior of black holes, but without actually having an event horizon or a singularity. One such object is a gravistar, which is like a giant bubble filled with a special kind of energy called dark energy. It has a solid surface instead of an event horizon, and it could theoretically mimic the gravitational pull of a black hole. Another idea is a boson star, made up of exotic particles called bosons. These stars could also be very dense and have a strong gravity, potentially mimicking some of the observational signatures of black holes. While these alternative explanations are intriguing, they're still theoretical and there's no direct evidence for their existence. The majority of astronomers believe that the objects we observe as black holes are indeed black holes. However, when it comes to supermassive black holes, the situation is a bit different. These behemoths are so massive that the average density inside their event horizons is surprisingly low, even comparable to the density of water. This means that the physics of matter inside a supermassive black hole is much better understood, and alternative explanations, like a cluster of very dark objects, are less likely to be stable enough to mimic their behavior. One of the biggest mysteries surrounding black holes is their connection to entropy, a concept from thermodynamics that describes the amount of disorder or randomness in a system. Now, the second law of thermodynamics states that the total entropy of a closed system can never decrease. This means that if you throw something into a black hole, the black hole's entropy should increase to compensate for the information that's seemingly lost. In the 1970s, Jacob Bekenstein suggested that black holes must have entropy and that it's related to the area of their event horizon. Stephen Hawking's discovery of Hawking radiation further strengthened this link between black holes and thermodynamics. Using the laws of thermodynamics, Hawking was able to confirm Bekenstein's idea and calculate the exact relationship between a black hole's entropy and its event horizon. This was a groundbreaking discovery because it connected black holes to the laws of thermodynamics. It also led to the development of the holographic principle, an idea that suggests that all the information about a 3D space, like the inside of a black hole, can be encoded on a 2D surface, like a hologram. One puzzling aspect of black hole entropy is that it's proportional to the area of the event horizon, not its volume. This is strange because entropy is usually related to the volume of a system. The more space you have, the more ways you can arrange things, and the higher the entropy. To understand this, physicists have turned to different approaches to quantum gravity, a theory that tries to combine the laws of gravity and quantum mechanics. To understand this, physicists have turned to different approaches to quantum gravity. In string theory, for example, scientists have been able to count the microscopic configurations or microstates of certain types of black holes, and the results match perfectly with Hawking's prediction. Loop quantum gravity, another approach, offers a geometric explanation for black hole entropy, suggesting that it arises from the quantum properties of the event horizon itself. While we've made significant progress in understanding black hole entropy, there are still open questions and challenges. For instance, we still don't have a complete theory of quantum gravity that can fully explain the behavior of black holes at the microscopic level. The black hole information paradox is a major headache for physicists. Again, information can't just vanish into thin air. Here's the conflict. Black holes are greedy. They swallow everything that gets too close, including information about the objects that fall in. But quantum mechanics says not so fast. One of the core principles of quantum mechanics is that information is never truly destroyed. It might get scrambled or hidden, but it's always there somewhere. So, how do we reconcile these two seemingly contradictory ideas? That's at the heart of the information paradox. Hawking radiation makes this paradox even more puzzling. Hawking's calculations suggest that this radiation is random and doesn't carry any information about what fell into the black hole. So, as a black hole slowly evaporates through Hawking radiation, it seems like all that information is lost forever. To make matters worse, there's another related puzzle called the firewall paradox. It suggests that if information is preserved in black hole evaporation, then there must be a firewall of high-energy particles at the event horizon, burning anything that tries to enter. This creates a conflict with Einstein's equivalence principle, which says that falling into a black hole should be a smooth experience, at least until you get really close to the singularity at the center. Physicists are still grappling with these paradoxes, and there's no single agreed-upon solution yet. Some believe that Hawking's calculations might be incomplete, and that the Hawking radiation actually does carry subtle information about the black hole's contents. Others suggest that the information might be stored on the black hole's event horizon. Black holes have now been brought into the realm of observation, thanks to the groundbreaking discoveries like the detection of gravitational waves and the first ever image of a black hole shadow. These incredible achievements have not only confirmed the existence of black holes, but have also deepened our understanding of their properties, their behavior, and their role in the evolution of the universe. We've journeyed into the depths of black holes. From their immense gravitational pull to their ability to warp space-time, black holes represent a frontier of scientific exploration where the known laws of physics are pushed to their limits. We've explored the history of black hole research, from the early speculations of John Mitchell to the groundbreaking discoveries of Einstein, Schwarzschild, and Hawking. We've witnessed the evolution of our understanding, from the theoretical predictions to the recent observational evidence provided by gravitational waves and the Event Horizon Telescope. Black holes, while once considered mere mathematical curiosities, have now become a cornerstone of modern astrophysics. They play a crucial role in the evolution of galaxies, shaping the cosmic landscape and influencing the formation of stars and planets. But the mysteries of black holes are far from solved. The nature of the singularity, the fate of information that falls into a black hole, and the potential for black holes to connect to other universes or even give birth to new ones remain open questions that continue to inspire and challenge scientists. If this exploration has ignited your curiosity, I encourage you to delve deeper into the fascinating world of black hole physics and astrophysics. Explore the latest research, learn about the ongoing efforts to observe and understand these objects, and ponder the profound implications they hold for our understanding of the universe and its fundamental laws. And who knows, perhaps the next big discovery in black hole physics will be made by someone watching this video right now. Your passion for science, your thirst for knowledge, and your willingness to explore the unknown could lead to breakthroughs that reshape our understanding of the universe and our place within it. Thank you everyone for watching. My name's The Big Why. Don't forget to drop a like, and if you're new to the Why Not family, a follow. And I'll catch you guys in the next video.